Hello. Today I'm going to be continuing my calculus, which I haven't done for math marathon in last week because of something else going on. So I'll do one today. I'm not sure how long it'll be, but I'm going to be doing these ones: integrating, polynomials, substitution, and then exponentials and trig. And if I pronounce anything wrong in this video, I really don't mean to. It's just a mistake. Okay. Integrating polynomials. Earlier we saw how integrals connect to various applications, including distance, averages, and most importantly, area under a curve. We also saw the intricate connection between derivatives and integrals, which are essentially inverses. We now turn our attention to evaluating general integrals. While we've seen that differentiation is usually responsible straightforward, integration is often quite difficult. This is analogous to how easy it is to multiply numbers, but how difficult it can be to factor them. To pose a comparison, think about the speed at which you can solve for 17 times 51 and how quickly you can get factor 867. Indeed, we'll see that in the upcoming lessons, many of our strategies ultimately boil down a bit to the guessing game. What is the antiderivative of x? It wouldn't be a plus, I believe. Yeah, it's gotta be all of the above, I guess. So since one, so yeah, plus c. We're calling that constants upon differing, so in the fact that these are all antiderivatives of x. Going ahead and differentiate each one to confirm this. This shows that anti-differentiation isn't a one-to-one process. We can shift by any constant. This is a common mistake to make. In fact, this is a subtle difference between an antiderivative of x and sum of x. The former could mean any of the above, with the latter refers to all of them simultaneously. In other words, if we ask for an antiderivative of x, we can answer 1 over 2x to the second, or 1 over 2x to the second plus 21, or 1 over 2x to the second minus 3. But if you ask for sum of x, we answer 1 over 2x to the second plus c, where c is a constant. So it's kind of related, but also kind of different with the constants included. The constant, when you're solving for a lot of those, the constant is not that important, especially for integrals, because in the end you just, you just end up deleting. Just getting rid of them. See. What is the value of 2? The sum of 2, 0, x derivative of x. So, let me try to think. I'm not sure. I'm trying to think. Maybe it'll be 1 over 2, but I wouldn't think so. But maybe. Or would it be 2? It's over either 1 over 2 or 2. So, So it would probably be, I'm gonna go with 2. Okay, yeah, that's good. Let me see why. Okay, sorry. For the last problem, we know that the antiderivatives of x are the form of 1 over 2x to the second plus c. Let me get a calculator quickly. For every constant c, then we obtain a sum of 2, 0. X derivative of x, 1 over 2x to the second plus c. And then we could go, which equals 2 plus c minus 0 plus c, which just equals 2. If c is 0, which it is. Because the c can't, R cancels. It would also find the picking the antiderivatives from the previous problems or other ones too. For instance, we used 1 over 2x to the second as an antiderivative of x. We get 1 over 2, 2 to the second, minus 1 over 2, 0 to the second, which just equals 2. So I wonder if that'll work for everything. Like just doing top number plus c minus bottom number plus c. Or would that always work? Or you should just minus them all together. I don't think that works all the time, especially for I don't think that would work all the time, especially for x's, so this is the power. That wouldn't work for. Okay. The simplest functions are polynomials, which turn out to be relatively painless to integrate. We'll explain that over the next few problems. We've already seen that sum of x derivative of x equals 1 over 2x to the second plus c. So for a constant positive n, what is sum of x to the n derivative of x? So n is a polynomial. Definitely. I know this would be a row minus 1. It would be either this or this. For a constant positive, so we probably wouldn't just be this, huh? And minus 1. Maybe not. I mean, would it be kind of the same how that's 1 over 2? I'm gonna go with it. Plus. Well, I guess it was close, but I guess if we wanted to be positive, it would just be addition. A derivative of 1 over n plus 1 x to the set. X to the n plus 1 is x to the n. So 1 over n plus 1 x to the n plus 1 plus c is that antiderivatives of x. So it could just kind of be the same. Yeah, just like that. I'm gonna look at this again, just to make sure. I guess I should have thought possibly would definitely be an addition. The previous problem allows us to integrate any polynomial. We saw in that one, it was just, no. Yeah, we can, okay. I wonder if we could just do it as 11x plus 2. Oh. It just seems like it would be 40. Would it be 40? Look at the last one. How does it relate to it? It doesn't really relate to it that much. Alright. Since the antiderivative probably like 80, 160. I guess I'll see why. Like, I can't just say, like, oh, like, I just got unlucky. Like, I have to admit that. I didn't know what it was. I was trying to make a best guess. Okay. The antiderivatives of 3x to the second plus 2x plus 2 are given by x to the third plus x to the second plus 2x plus c by the previous problem. So, yeah, it's basically undoing it. So, yeah. Well, at least I gained that knowledge now. It's a little hard because they always come up with a new answer that is something that, like, I didn't gain previous knowledge on. So, it's just, like, the opposite because I guess you could go on and eliminate the x's if you wanted to do another derivative of 3x to the second plus 2x plus 2, and you eliminate 2 and stuff. But I guess it's opposite, so more like increases. Like if you're going into like the past, which you probably could find a derivative easily. Taylor series definitely helped me with that. So, if x equals 5, the antiderivative is 160 plus c. And at 0, x equals 0, the antiderivative is just c. So we obtain 5 over 0 through x to the second plus 2x plus 2 derivative of x equals 160 plus c minus c equals 160. And I guess we're doing the distance, and c's you can eliminate, so they're not as important as you think, so it's just 160. It goes the same for like e to the x. When you do that, they have c's too. Basically everything in this has c's, but usually they just eliminate. So let me try to get this question right. We've seen that the antiderivative of x to the n is 1 over n plus 1, x n plus 1. Nothing about this requires n to be a non-negative. Integer is the polynomials, so actually we can integrate a somewhat broader class of functions. Using this, compute for 1 x 1.5 plus x minus 2 derivative of x. So, we want the antiderivative that. What antiderivative mean? X to the 1/5 power. It's a little weird to do that. I mean, it's usually one more power than another number, the previous. It's weird since it's a decimal. So, but it is 4, 1, 2. No hints either. So it make it even harder. Let me see if this calculator can come in handy. I'm not gonna try to cheat there, but just make sure. So we kind of just want to undo it. So let's just do y as an example. X is 4 to the 1. To 8 and then 4 to the 2.5. Okay, I guess that will arguably work. So 4, 2.5, and 2 4 to the negative 2, which is a positive. Yeah, it is. 4 to the negative 3. Oops. 4 to the negative 3. Would that be kind of considered? Like, maybe. Like, I wouldn't argue about it. It's, like, would it go down or would it go up? This is going up. That will probably go down. Or just. So it would have to be that, right? And then could we just do 32 divided by 3? Well, nah, like including all the other ones. I don't need to do this one. It doesn't just go on with it. But if we add those equations, wouldn't it be I don't know, all these questions, all these answers. Maybe I just don't know what I'm doing, but. So, what is 4 to the negative? I guess we should label it as x, right? But it considers this answer. One, two. I really don't know what it would be. C's will eliminate. Okay, 3. 4 to. Would it work like that? I'd just be having it. Oops. Yeah, I still know I really need to learn this more. So, this got 160. The anti-charge were increasing in power. None of these had any negatives either. I can't really branch. Is there anything I could use? I think it would be 12. Obviously, I'm just seeing how to cringe at. So the anti-derivative of x 1.5 is 1 over 2.5x to the 2.5 plus c equals, it would be c, 2 over 5x to the 2.5 plus c, which are basically the same. So integer to negative 2. Of course. It's negative 1 with negative 3. Let me answer the same equation. So, integral integer negative. Oh, it's a positive number, right? So it'd be negative. It's a negative 1. You see, that x equals 4 is 12.55 plus c, x equals 1. These points 4 and 1. That's how we can say it. I wonder if we could do it the other way around. Maybe, but not what I saw. Thus far, our integrals have constantly incorporated specific bonds, such as 1 and 4. However, it is entirely feasible to leave one side or even both sides unbounded. This approach might be applicable in situations when we need to travel uncertain, for instance, how far a car would travel before coming to a halt. These are called improper integrals. We take them as fitting the sign of the appropriate bond. How do you evaluate this infinite integral? Just give me a second. Let me look at this. I'm still confused about this. Wait, let me see this. 1. Okay, 1. X equals 1. Equals negative 1. Negative 1. Negative 0.6. Is this for the whole equation? So let me do this. 2 over 5 times 1 to the 2.5 power. Divide by 5. Oh, sorry. So 2 divided by 5. Times 1 to the 2.5 power minus 1 to the -1. Oh. I guess we learn something new every day, huh? Yeah, that's how it works. That's actually right. When x equals 1, x equals 4. It's actually like super good. I'm definitely gonna take a picture of that. Take a picture of this. Just to prove that it's right. It's interesting. Finally feeling normal now. No, this crazy math. I still like it, and it doesn't mean I hate it, but it's still crazy math. Now, I'm sorry I got off track. Continue with what we were mainly here for. Infinite integral. How do you evaluate this infinite integral? As I was saying over here. We evaluate it by simply as the limit of finite integrals using this definition. The limit, or the sum of infinite a function x derivative of x equals limit b is infinite b over a function x derivative of x. So replacing with b, and then, or b, sum of b negative a function x derivative of x, and the limit of a negative infinite. So just replacing with a placeholder. So with this definition, what is infinite? 1 over x to the derivative of x. So the antiderivative of that would actually just be it used to be x to the third power, antiderivative. 1 over x to the third power. Or would it be 1 over to the x to the 1 over x to the third power, x to the third power? So let's do 1. Let's just say when x equals 1. So we're doing 1 over 1 to the third power. The third power. What should that be? 1 times. Oops. Mm-hmm. 1 divided by 1. 1 divided by 1. The third power. Times 1. Yeah, wouldn't it be arguably 1 to the third? 1, I guess. Well, I guess I could have said that from the start. But let's hope my math is right. Okay. In the last problem, we saw that the antiderivative of 1 over x to the second is, well, I was wrong with that. It was negative 1 over x plus c. Thus, b, 1 over x to the second derivative of x equals negative 1 over x plus c equals negative 1 over b plus 1. And then if we go here, the limit of b is infinite, negative 1 over b plus 1, which just equal 0 plus 1, which should equal 1. I guess it would be the plus c, and it would be technically 0, which is perhaps surprisingly a finite number. What is the value of this integral? Infinite, negative infinite. Okay, hint. And define it in power. Well, we just arguably be 0, improper, or does not exist. Okay, go with 0. It does not exist. There's a substance distracting that we made here. The definition of infinite, negative infinite, function x, derivative of x is not limit a, infinite a, negative a, function x, derivative of x. As you might think, but rather is defined by infinite, function x, derivative of x equals limit a, negative infinite, and continuing on. When you take the inner limit, you get infinite. When you try to evaluate the outer limit, you get an infinite minus infinite situation, which is undefined. Recall that acceleration is a derivative of velocity, which is turned to the derivative of position. Suppose a car's acceleration is given by function t equals t. Which of these could be a car's position at a function of time? So, a function of time. You'll have to be in order. In good order. Yeah, next thing for me. For every constant c, the velocity of the car is given by the antiderivative of the acceleration, which is 1 over 2 t to this. Oops. Where was I? Hopefully I didn't restart it. Maybe. So for a new constant c2, the position of the car is then given by the antiderivative of the velocity, which is 1 over 6 t to the third plus c1t plus c2. These two constants could potentially be anything, so only the choice 1 over 6t to the third plus 1 over 3t plus 1 over 2 gives a possible function. An important question to ask is what C1 and C2 should be in context of the car's travel. And the next one, which of these is an antiderivative of 1 over x? One antiderivative? Antiderivative. So it would have to be 1. I really know get a number above. You always have to test the quizzes, and it's never right on those. That's why I never answer this. Like, they always just come up, and it's obvious if the teachers want an extra choice to make it 4 choices. But, in earlier lessons, we established that the antiderivative of xn stands as 1 over n plus 1, xn plus 1. However, for n equals -1, this formula does not prove existence, as we are necessarily left with a denominator of 0. In fact, without pre-existing knowledge, answering this question isn't quite standard. We'll delve into this more definite substantive lesson. For the time being, it is a quick to bear in mind that the derivative of 1 results in 0, and I know that, luckily. The derivative of 2 over x to the second outputs -4 over x to the third. I didn't know that. And the derivative of infinite doesn't necessarily hold any substantial meaning, though it should theoretically be 0. Therefore, none of the choices provided just will be an antiderivative of 1 over x. In this lesson, we took a deeper look at integrating some easy functions, naming polynomials and similar functions. In doing so, we also saw how we integrate over an infinite length interval. And in the coming lesson, we'll start to look at increasing complicated functions and develop additional strategies to integrate them. And finish the lesson. I wonder if I could check how long. Oh man. No. Sadly, no. I would like to know, but intriguing. Well, I have no idea how long I'm going for. Well, I will. Right now, definitely. So I'll go to substitution. Not substitution, right? Reverse exchange rule to compute challenging integrals. Now we're reversing the exchange rule. The exchange rule was already. We've now seen how to use the FTC to evaluate integrals of simple functions. Simple? Well, I guess they're like simple, but like the rules aren't. Simple functions, quote unquote. Namely polynomials and the like, for example, variables raised to non-integral powers. Now we'll use the tools to integrate some of more complex functions by substituting in and transforming complicated functions and functions we know and how to deal with. We've seen before that antiderivative of cosine x is sine x. Which of the following is the antiderivative of cosine 2x? Antiderivative. What is the antiderivative? Cosine 2x. Remember the exchange rule. We would work the same way around her. 1 over 2. I picked that. We call that derivative of sine 2x is not just cosine, but 2 cosine 2x. Thus, the antiderivative of cosine 2x is 1 over 2 sine 2x. As usual, all the antiderivatives are given by 1 over 2 sine 2x plus c. In this lesson, we establish sum of x to the a derivative of x equals 1 over 1 plus a, x to the first plus a plus c, comma a is not equal to negative 1, which allows us to find antiderivative of square root of x. So, yeah, we don't want negative 1, definitely not. Which of these is the antiderivative of x? Square root of 1 plus x to the second. So antiderivative, and it won't be negative 1. Antiderivative. So we would increase, but we checked all of them. I wonder if it'd just be doubling it. But then, on the other hand, that would make it too big. But antiderivative would just be this. 1 over 3. That would be 1 over 2. I'm gonna check why. In the loose sense, the antiderivative formula suggests that integrating the square root of a quantity represents an expression involving the same quantity raised to the third over 2 power. We therefore make an educational guess about the antiderivative of x square root of 1 plus x to the second. It should be proportional to 1 plus x to the second 3 divided by 2. Let's write function x equals a parentheses 1 plus x to the second parentheses 3 over 2. Taking the derivative using the chain rule, we find function prime a equals a times 2x times 3 over x, 3 over 2, square root of 1 plus x to the second, which equals 3ax, square root of 1 plus x to the second. If we choose a equals 1 over 3, that we see that function x equals 1 over 3, 1 plus x to the second times 3 over 2. It's the antiderivative of x square root of 1 plus x to the second. In the last couple problems, we saw that the chain rule led to many functions like x square root of 1 plus x to the second being easily antidifferentiable, while others like square root of 1 plus x to the second are much more difficult. In the rest of this lesson, we'll explore how formally this is introducing the idea of substitution, which is essentially undoing the chain rule. To use substitution, I'm probably pronouncing it like substitution, not like substitution, not subtraction. To use substitution, you are used as a convenient function of x. Ideally for one for which du, or derivative of u, also appears in the function you want to antidifferentiate. For example, antidifferentiate x square root of 1 plus x to the second, we write u equals 1 plus x to the second, so that d derivative of u equals 2x derivative of x, which implies, as we see in this equation, function x derivative of x equals square root of 1 plus x to the second. X derivative of x equals 1 over 2 square root of u derivative of u. And thus the function we need to antidifferentiate becomes 1 over 2 square root of u derivative of u. This is much easier to antidifferentiate, being 1 over 3u. It's 3 over 2, and then we only need to substitute 1 plus x to the second back in for u to get the final answer, 1 over 3, parentheses 1 plus x to the second, 3 over 2. Let's find the antiderivative of x negative x to the second. What substitution should we use? So, u should equal, would it just be the same? Negative x to the second. Why is that? Remember, we want to use a u for which derivative of u also appears in the function we are antidifferentiating. We use u equals negative x to the second. We have d derivative of u equals negative 2x derivative of x, which essentially appears in the function. So let's rewrite the function. Negative 1 over 2 e to the u derivative of u. So that makes sense. We have antiderivative. Using the substitution u equals negative x to the second from the previous problem was the antiderivative of x e negative x to the second. Antiderivative. Antiderivative. I guess we could make it negative. Like this. So close but so far at the same time. This is honestly very hard, but be honest. We need to perform the integral sum of xe minus x to the second equals derivative of x. Using u equals negative x to the second by taking the derivative of u with respect to x, we find derivative of u equals negative x derivative of x, or negative 1 over 2 derivative of u equals x derivative of x. Substituting this expression together with u equals negative x to the second until the original integral gives us, as we see below. You could pause it if you want, but this is as we simplify. There we go, simplifying, moving stuff around, changing it, simplifying it totally, then getting rid of. Okay, up top, ordinary constant. Substituting x gives us, substituting x back in gives us negative 1 over 2e negative x to the second. Let's find the antiderivative sine to the third x cosine x. Which substitution should we use? So, I would say just sine. Well, literally just sine, and then sine to the third. So we just want to find the antiderivative or derivative. Really good. An antiderivative. More math. I shall label this like way too much math for a tired boy on a Friday. Using the substitution u equals sine x from the previous problem, what is the antiderivative of sine to the third x cosine x? What is the antiderivative would be? Well, it was like, it's gotta be 1 over 3. I'm just gonna be annoyed if it isn't. I'm rushing through these and I just yeah. Like, could I just technically have done that with this calculator? Because it does contain sine. So sine. Let's just do sine. I don't know how I would do this on this. Sine 1 third. Yeah, well, no. Let me just do the explanation. I'm not sure. When u equals sine x and thus the derivative of u equals cosine x derivative of x, the function becomes u3 derivative of u. And the antiderivative of this gives, this is 1 over 4 u4. Substituting back for u gives us 1 over 4 sine to the fourth x. Up until now, we only been able to find antiderivatives. Because of FTC, this allows us to evaluate definite integrals, but we need to be careful. For example, consider the following argument for a value pi sum of pi 0 sine 2x derivative of x. We can't use this u substitution of u equals 2x because derivative of u equals 2 derivative of x. We write sine 2x derivative of x equals 1 over 2 sine u derivative of u. Now we need to evaluate pi 0, 1 over 2 sine u derivative of u. By the FTC, this is equal to 1 over 2 parentheses negative cosine u parentheses pi 0 equals 1. However, this graph shows that pi, or sum of pi 0 sine 2x derivative of x should be 0. Which step was incorrect in this above argument? Is there even a 4 in it? Why do they have 4 things if there's only 3? So the step was incorrect in the above. Should be 0. Probably 2. Because it's a 2. Should be 0. 3. Okay. The first 2 steps are just defining a good substitution to make. Indeed, u equals 2x is a very reasonable substitution. The mistakes occurs in step 3. We blindly make the substitution the integral without taking the bonds into account. Writing u equals 2x, we need to remember this, as since x ranges from 0 to pi, we now ranges from 0 to 2 pi. Thus, the correct integral is actually the answer. The sum of 2 pi 0, 1 over 2 sine u, derivative of u equals 1 over 2, parentheses, negative cosine u, 2 pi, 0 equals 0, as expected. His derivatives and integrals are inverses. Every rule for derivatives should have a corresponding rule for integrals. In this lesson, we saw the exchange rule and can be used in reverse when we need to integrate the function of the form function prime, parentheses, derivative, gx times g prime x. A good clue that substitution will be useful is when we are integrating a function times the derivative of that function or a part of it. So the last warning, be very careful to update the bonds when performing substitution. As we saw, failing to do so can potentially lead to nonsense results. And we finished that. That was a quicker lesson. So let's do exponentials and trig. Dabble with transtangential integrals. See if this will be quicker, hopefully. In the first lesson in this chapter, we saw that the general antiderivative of xn is 1 over n plus 1, x to the n plus 1. For n equals negative 1, this formula breaks down as this should result in a 0 denominator. Thus, we have to figure out whatever way to find the antiderivative of 1 over x. Suppose function fx is the antiderivative of 1 over x, for which f1 equals 0. Given the graph of 1 over x, what is the value of f2? So f1 equals 0. So it would be negative. Minus 0 equals fine. f2 minus f1 is f2 minus 0. Clearly the integral is positive, as there is positive area under the curve between 1 and 2 as seen in the graph, so f2 is positive as well. If fx is the antiderivative of 1 over x, and f1 is 0, what is the value of f1 over 2? Wouldn't it be negative? Okay, good. As before, sum of 1 over 2, 1 over x derivative of x equals f1 minus f1 over 2 equals 0 minus f1 over 2, which would equal negative f1 over 2. Is positive according to the graph, so f1 over 2 must be negative. By continuously applying this type of reasoning, it is observed that fx is negative by 0 is less than x is less than 1, positive for x is greater than 1. This graph is visually represented like this. This reminds us of the log function. Indeed, we recall that derivative of a log function is 1 over x, so we have found the desired antiderivative. There is one caveat. F should make sense for negative numbers as well. but the log function is only defined on positive numbers. This means we need a slight adjustment, nothing that for negative numbers to the derivative of log negative x is 1 over x, as well by the chain rule. So we can say this. An antiderivative of 1 over x is log negative 1 for negative x, and an antiderivative of 1 over x is log x for positive x. Now that makes sense. More succinctly, an antiderivative of 1 over x is log absolute value of x. Here we assume the base of all logarithms is e, unless explicitly stated otherwise. In other words, log means a natural logarithm. Using an appropriate u substitution was antiderivative of 3x plus 6 divided by x to the second plus 4x minus 3. What is the antiderivative of it? So it would be absolute, which these are all pretty much. It has to be 1 over 2, though. They're all pretty much the same. It's just whatever is log. Let me see what the use would be if it was. Where is log? Okay. So, just consider it 1. Log 1 to the second. I'm also doing number b. B. So 0.3 times 1. And 1 plus 6 divided by yeah. I don't think we can relate to each other. You can't copy it. I need to do 3 over 2 long. Over 2 long. Okay, 1. I'm not sure, arguably. Out of all of these, I think it would honestly, if it was, it would. So it would have to be this. Okay, good. We've implemented that the substitution of u equals x to the second plus 4x minus 3, such as derivative of u divided by derivative of x equals 2x plus 4. This is typically a complex substitution, but we can be identified by judiciously applying for the strategy outlined at the conclusion of our previous lesson, which entitled expressing the function of form 1 over something times derivative of something. The function that comes, as we see in this, I'll read it for a second, can simplify down to 3 over 2 times 1 over u, derivative of u over derivative of x. The antiderivative of which 3 over 2 log absolute value of u substitution back in gives 3 over 2 log in the equation, which is our answer. This method of substitution combined with logarithms can be used in trigonometry as well. Using an appropriate u substitution was the antiderivative of tangent. Antiderivative of tangent. Okay. I guess we can't really. Oops. But, was it antiderivative? Antiderivative. Well, it would be sine, I know. So it would have to be the cosine. I thought it would be sine. I was like, it's definitely B or D. I was off on that. We use u equals cosine x so that du equals negative sine. So when we use it that way around, I always see sine as more important, not to the cosine. But I like cosine more, but I feel like sine is sometimes used more. So I take that as the most important. But I was wrong. And yeah, we do getting back. Okay, now let's head to the next question. Recalling from the first lesson that the area under the curve 1 over x to the second for x is more than 1 is actually finite. Would we expect the area under 1 over x for x greater than 1 to be larger or smaller? So it's finite, it's real. Area under 1 over x. Under, if x is more than 1, smaller than? X is more, x is for x is more, we expect our curve to be, or it might be, which is referred to the next question. Whatever. What is a sum of infinite 1 over x derivative of x? No problem. There's a limit. So I approach the infinity. Okay. Recall as we saw equals limit b is infinite b, sum of b1. To simplify, not infinite. To calculate b1, 1 over x derivative of x, we know that the antiderivative of 1 over x is log. Thus we obtain b1, 1 over x derivative of x equals log x, b1 equals log b minus log 1, which equals log b. The value of the improper integral, therefore, limit of b infinite log b, which approaches infinity. This is a little surprising integrally. Even though the function goes to 0 as x approaches infinity, the area under the function is finite. Trigonometric functions are usually pretty difficult to antidifferentiate, and we won't go over all the tools here. One trick is substitution, as we've seen a bit of already. Using substitution was the antiderivative of cosine x e sine x. So it would just be e, to be honest. So it would have to be e. So, I guess, I know, e. Always e's derivative is e. But I'll just get. With u equals sine x and derivative of u equals cosine derivative of x, the function between e to the u derivative of u and antiderivative with a simplify eu equals e sine x. We saw earlier that functions like sine 2x and cosine 2x are easily to find the antiderivatives of, so a common trick is to write trig functions in terms of those. So what is the antiderivative of cosine to the second x? So let me just get the hint quickly. We have cosine 2x equals 2 cosine, or 2, we have cosine 2x equals 2 cosine to the second x minus 1. Antiderivative then? This one, it have to be plus. And 1 over 2. 1 over 2 or 1 over 4. Okay, good. Note that we obtain cosine 2x equals, so we see 2 cosine to the second x minus 1, which goes to cosine to the second x, which goes cosine 2x plus 1 divided by 2. We saw earlier that 1 over 2 sine 2x is the antiderivative of cosine 2x. Therefore, our antiderivative of cosine to the second is 1 over 4 sine 2x plus 1 over 2x, as we get the plus 2. And I guess that's it. Sorry I was rushing through the end. But I don't know, I just did. And now we're finished. That was good, to be honest. I'm getting better, even though it's still kind of hard. It's getting better. That's good. And that's going to be it for today. Thank you so much for watching. I would appreciate any answers or comments or anything, like fixing anything. I know I did some things wrong, especially some things I were confused on. So if anyone can say anything to help me, I would really appreciate it, a lot. It just helps me learn and grow better. Well, I appreciate you for watching. Hope to see you next time. Thanks for watching. Goodbye.